Okay, hi everyone. We're going to have some notes today on starting a new unit on circuits and starting with the first component, which is capacitors. And before we do that, I just want to show you kind of a fun electrostatics video. Watch closely and see what's happening in this security video from a gas station fire. Sorry, security video from a gas station. I'm tired. Okay. And watch what she's doing. Watch all the details of what she's doing. You notice she keeps touching her clothing. Now she's sitting on the seat in the car. Sat down again, got up, sat down. Okay, now she's pulling on her sweater. Okay, so what happened there? See if you can explain that. Pause the video and explain it. Okay, so hopefully you can see that she was doing a lot of separating charge, and she probably was in a really dry area where this charge was building up on her. And when she touched the metal of the car, she discharged. She grounded herself, but it was not a good place to make a spark because it was right next to the gas tank. So if you ever feel that you might be charged on a real dry day, and you're concerned about touching something that might cause a spark like that, think about where else could she have grounded herself besides right by the gas tank, and then she could touch the gas tank safely. So some gas stations actually have a place you can touch before you pump gas to ground yourself. Um, or she could have just touched anywhere else on the metal of her car to ground herself first. Okay, I also, we use the Van de Graaff generator, which is in the classroom. And it was too big, I couldn't bring it home, but I thought I'd show you a video of the same Van de Graaff generator we have and some of the demos that can be done with it. This is from the Educational Supply Company, so you'll see.
This unique hand crank model Van de Graaff generator is not only affordable, it also helps dispel some common misconceptions about this familiar museum device. The accumulated charge in the dome can be used to demonstrate a large number of electricity and electrostatic concepts using simple accessories and household items. Just like plug-in models, this Van de Graaff creates a large static charge on the dome by separating charges at the bottom of the column and using a moving belt to deposit them at the top. Because the belt is moved manually, students won't get confused about the source of charge on the dome. The big question is, will it stand my students' hair on end? The answer is yes. Just make sure the students aren't grounded. Standing on a plastic milk crate does the job. We're demonstrating this concept with the electric plume. I'm going to place a small rubber ring on top of the generator and add some puffed cereal. When you crank, the cereal stands up and eventually pops off. You can also place a fluorescent bulb close to the dome. When I crank, the dome will discharge and create enough electricity to light up the bulb. If I place a few aluminum pie plates on top of the dome and turn the crank, electrical charge will be transferred from the dome to the top plate. When it has accumulated enough charge, the top plate flies off. As I continue to crank, the other pie plates soon follow suit. Using this generator in the wintertime, when the air is dry, really increases its effectiveness. As the humidity increases, the success of these demonstrations will decrease. When I get this out in my classroom, the students are really drawn to it. It really makes science fun.
So those are some of the things we do with the Van de Graaff, and we also do some other things. We have a bunch of students hold hands, and the charge transfers to all of them. And if they have some tinsel taped to their face, you can really see the tinsel spread apart and and rise up, kind of the way he had his little demo of the thing that's all little bits that spread apart when they got charged. Okay, so that's it for electrostatics right now. Now we're going to talk about capacitors. And you have this handout on the assignment sheet. There's a handout that you can put your notes on, or you can just write it in your notebook. So a capacitor is a device that stores charge. And the capacitor is simply made of two parallel plates. They're conducting material, and in between there's an insulator, so that charge cannot jump across. This is really different from a battery. A battery pumps charge across, but the capacitor keeps the charge apart. And often those two plates, can be really large because they're trying to store a lot of charge. And so they're folded and rolled, and they get put in a can, and it ends up looking like this, like a cylinder. Looks like a battery. It's not a battery. I brought some capacitors home to show you from school. This is a 1 farad capacitor, which is huge. It used to take an entire room to make a capacitor this big, but the technology is amazing. This is a 330 microfarad capacitor. This one is a 100 microfarad. So they all say something on them that tells you 220 microfarad. They're all different values of capacitance. The circuit symbol for a capacitor is the two parallel plates with the lines that represent the wires coming out of them. All right. So the other thing to think about with a capacitor is that the two plates are going to be charged, opposite charge, plus and minus, and the charge won't be able to jump across, even though it would like to. They're attracted to each other, and that's why the charge stays. That's why it stores charge. And it also creates an electric field. As you know, there's going to be an electric field with field lines going from the plus to the negative, positive to negative plate. And so these are the blue field lines showing the direction of the field, and it's constant through the whole capacitor, inside the capacitor. The electric field is the same everywhere, as we looked at in the electrostatics unit. Okay, so here are some notes I wrote about. Here's the design of the capacitor again with the two parallel plates. When they're charged with a voltage, the higher voltage is the plus, the lower voltage is the minus. You can connect those two plates together with a wire, which will allow charge to flow, and it will flow through the wire. And if you put a bulb there, it'll flow through the bulb, and it will light the bulb just while it's flowing. And then as it's flowing, it's discharging the capacitor, and so this voltage will actually go down over time. You can see here, here's kind of a graph showing the original voltage difference along this is like the wire here. The voltage is high at the plus, going down, down, down until you get to the minus, and it's low voltage. But as it discharges, the voltage along the wire is starting from a lower voltage, and eventually the two voltages are both going to be the same. The equation for capacitance is charge per voltage. In other words, how much charge can you store given the amount of voltage that you've put on it? So the bigger the plate, you can imagine you're going to be able to store more charge for a given voltage. So bigger plate area. It also has to do with the distance between them. It also has to do with the quality of the insulator, the dielectric. That capacitance is a property of the capacitor. So every capacitor has its capacitance, like I was reading off some of the values from the capacitors I just showed you. And that's how much charge they can store when you put a given voltage on them. The other main equation for capacitors is this one, which tells you what the capacitance is based on how big it is, the capacitor, the area, surface area of one plate, the dielectric constant, it's called permittivity of the insulator or dielectric, and the distance between them. So those are the two main capacitor equations. And this C equals Q over V is often also written Q equals CV. And you could think of it as a linear equation where the capacitance is the slope of that line. This is the handout you could be writing your notes on right now, or you could write them in your notebook. And this is posted on the assignment sheet. Okay, so looking at this equation again, just so you understand that the capacitance does not depend on Q or V. The capacitance shows the relationship between Q and V because the capacitance is fixed for a given capacitor. The capacitance rather depends on these other things: the area of the plates, the distance between them, the permittivity, which is this number for air, or else for other materials it's usually some number times that constant. In other, for example, I have a table of them here. For example, something like polystyrene, you would multiply this number by that other constant, this constant here, which is the one for air. Okay, do this example, which is at the bottom of your handout. Try it and then pause your video because I'm about to tell you the answers. So you can pause your video now. Okay, so for the first one, I got 2.95 times 10 to the negative 9 farads, or 2.95 nanofarads. For the second one, I got, using Q equals CV, I got 7.67 times 10 to the negative 9 coulombs, or 7.67 nanocoulombs. So we've made these in class. I just found some pictures online of ones that simple ones you can make. This is a parallel type capacitor like I've been showing you pictures of. This is a Leyden jar capacitor where it's still basically two parallel plates with an insulator. The one parallel plate is the tinfoil on the outside, and then the insulator is the plastic container, and then the second parallel plate is the water inside, which is conducting to this nail. And so you basically have nail and outside, and if you touch those two together, you'll discharge it. And this is the type of storage jar that was the first type of capacitor, and it was used by people like Benjamin Franklin to store the charge from lightning bolts. Okay, so the Wimshurst machine actually has two Leyden jars. That's what these two things are. And when I crank it, I'm separating charge into the two jars, plus and minus, and when I bring this together, the spark is a way of them discharging to each other. And I can do the same thing with this handmade capacitor. I'm going to touch the capacitor to the two sides of the Leyden jar, of the Wimshurst machine, while I crank the machine, so that I'm not just charging the machine, I'm charging the capacitor too. I don't think you can see that I'm touching these right here. So now it's charged, and I'm going to touch them together to discharge it. And I got a little spark. Another thing I can do is charge the capacitor. I'm going to try to do this so you can see what I'm doing. Okay, you may not be able to see what I'm doing, but I'm just going to charge the capacitor again, and then I'm going to use it I'm going to discharge it across this little bulb over here. So watch the bulb, and you see it light. So that bulb actually takes at least 90 volts to light. It's a really high voltage, low current bulb, and that's why it's perfect for something like a capacitor. You would not be able to light an LED with this capacitor. By the way, you might be wondering what the dielectric is in this capacitor. It's just one of these polystyrene takeout containers. It happens to have a pretty good dielectric, better than paper or cardboard or something like that. Okay, so that's it. Try some of the problems, and I'll see you next time.